Good old Ann Surkey. My screen is frozen. Thank you, Captain Obvious. I should have figured that out. Appreciate that. So on your test, you're going to be getting questions involving time dilation, time changing, length changing, and mass changing. And in all of them, it's fair to ask you to find the original with the 0 or the new one or the v inside the equation. Here, they're asking me to find a length. Are they asking me to find L0 or L? Because that's really the tricky part here. Yeah. Okay, they're asking me to find the relativistic length. You know what? Let's change colors, Mr. Dewick. They want me to find that because we said L0, LO stood for the original length. So the original length is 620 meters. V is apparently 96% of the speed of light. And our length equation, let me know if I'm wrong, I'm going from memory, but I think it's L0 times the square root of what we called the gamma or Lorentz factor, that 1 minus square root of v, that thing there, yes? So it's going to be 620 square root of 1 minus 0.96 c over c. Jared, getting ready. Here's your cue. Jared, is there a c on the top? Is there a c on the bottom? Then they cancel. Now, what if there wasn't? Then, Jared, I would have meters per second on the top, and I would have to put 3 times 10 to the 8th meters per second as a number down there and just divide it and see what I got on my calculator. Square that decimal. There will be a couple of those on your test. Usually, I'm going to give them to you as a percentage of the speed of light, but I'll probably once, maybe twice at the most, give it to you in meters per second. For now, I think I can type this on my calculator. I've got a pretty good calculator. It's going to be 620 square root of 1 minus, I think it's just going to be 0.96 squared, all in brackets. Do you get, oh, holy smokes, that worked out, I can't say evenly, but without a lot of decimals. Is it 173.6? Yes? So if you got that, you get 2 out of 2, or you could have said 174. Otherwise, I would give you a half mark for the correct equation, 1 mark for getting the numbers in the right place, because I think the trickiest part is it L or L0? And then a half mark for the answer. Is that okay, Evan? Evan, in number 2, what are they asking me to find? L or L0?
L0.
The original length at rest? In fact, I'm going to argue that number 2 is identical to number 1. In fact, if I was clever and had technology, I could just paste the same work, change that, and change that. Change that, and change that. And I guess change that. Isn't that neat? Don't you wish you could do that? Yeah, shut up. L0 is going to be, apparently the original length was 45, and now we're traveling at 98% of the speed of light, so it's going to be 45, 98% of the speed of light. I think this one almost worked out nice. 45 square root of 1 minus 0.98 squared. Yeah, 8.95, almost 9 meters, a little less than 9 meters. Again, 9.0 I would take. 8.9, I'd take a half mark off, and I'd say learn to round off properly. 8.955 I'd take. 8.9549 I'd take. My rule of thumb, Robbie, if I'm not sure, I go to 3 sig figs is usually my rule of thumb. Although here, because it worked out to 173.6 even, I went to 4 sig figs. Could you maybe like open your binder and get your stuff out? Follow along? Yeah, Cody, talking to you. 8.9, did I say 5 or 6? 5. Same marking scheme as before. Number 3. Well, they're asking me to find a mass. Are they asking me to find M0 or M? Because the M at speed 0, the original mass is 65. Our speed is 0.99 c. If you were away last day, please make sure you have added this equation to your purple formula sheet in the relativity section, because Mr. Dewick, like a complete foolish young man, forgot to add the mass equation. I think the mass equation is the same as the time one, except with m's everywhere. Yes? Is that right? I'm going from memory. Is that, yeah? I already got the m by itself Yay! So, Mariah, it's going to be 65 divided by the square root of 1 minus 0.99 c over c all squared. Jared, is there a c in the top of the fraction? Is there a c in the bottom of the fraction? What's the word I'm looking for? There you go. Okay. And you'll notice also where, Jared, showing a little less work. If you're comfortable with your calculator and you can get to the answer from this, I'm good with that. We practiced enough that most of you are there. So I'm going to go 65 divided by square root bracket, 1 take away 0.99 squared. Does mass increase or decrease as you speed up? As you speed up, do things get heavier or lighter? Heavier. That's one of the reasons why we can't get to the speed of light. Turns out to get to the speed of light, you get an infinite mass. So you need more energy than there is in the universe to get more mass than there is in the universe. We can't get to the speed of light. 461 kilograms, I'm going to say. In other words, the fact that I got a bigger answer didn't surprise me. It made me go, yeah, I knew that was going to be bigger. Same marking scheme, half mark for the equation, 1 mark for the numbers, half mark for the answer. Next page over. Those of you that are nerds will notice that I actually did look up the length of the Starship Enterprise according to the Wikipedia page, and I made sure that you get the right answer. I reverse engineered the numbers to... Okay. They're asking me to find a length. Are they asking me to find L0 or L? Sorry? Someone said it. No? Okay, maybe. Sorry? L0? Oh, yeah, because this is the speed when it's moving. I'll take LO, either or. By the way, if you really want to impress me, because I had a British physics teacher, if you said L naught, because that's 0 is a naught in Britain, I might slip into that once in a while. They're asking me to find the original length, which is how I taught you to remember it. I'm good with that. So that must mean this length is 144. Speed is 98% the speed of light. For those of you that are nerds, this is the length of the Enterprise C, which was the next generation ship, as opposed to the original Enterprise, which was shorter in the original series. But as the series has got better, the ships also got larger. Hashtag nerd trivia. Okay. Well, Jared, the equation is this. But you told me I'm trying to get this by itself. How would I get that by itself? What's the square root doing to the L0? Adding, subtracting, multiplying, or dividing? So, Evan, how would I move it over? I'm not going to bother putting this one on my formula sheet because I think I can derive it in my head from the equation. So if I hear you correctly, and I think I do, you're telling me if I want to find the original length, take the relativistic length and divide. I would say to you, you are correct. So it's going to be 144 divided by 1 minus 0.98 squared. Jared, I already canceled out the C's, so I didn't give you your moment of attention there. Sorry. I know you're looking forward to it. It's going to be 144 divided by square root answer bracket. 1 minus 0.98 squared. 700 and I'll call it 724. I think according to Wikipedia, it's 725 meters long. That's big. Although the International Space Station right now is already 100 meters long. It's the size of a football field. But that's mostly its big solar panels. The actual where they live is much, much shorter. I would love it, Cody, if in your lifetime we did have ships that were nearly a kilometer long that people lived on permanently. That'd be cool. I want the Star Trek universe someday, not the Star Wars universe someday. Nerd, yeah. This time, because you rewrote an equation, Jared, I would probably give you 1 mark for the equation, half mark for the numbers, and half mark for the answers because you had to do some algebra first. A friend borrows your red Ferrari spaceship model X119, capable of traveling at 95% of the speed of light. The Ferrari is measured to be 5.6 meters high and 18 meters long. Yeah, I took this right from the homework. How long would you say the Ferrari is as it sped by you? Okay, this is asking me to find how long. Jaden, is this asking me to find L or L0, the original length or the relativistic length? Just L. So that L0, oh, am I going to use the 5.6 or the 18? Yeah. in the direction you're traveling. So if you can imagine, I think the Lamborghini would look kind of like that. The long part will be traveling forward. I'm going to use the 18. And that's why, remember, I showed you, it'd be like you were shrinking, making a photo look really, really skinny. That's what our eyes would see if we could see it that fast. V is 95% of the speed of light. So, Jaden, if I hear you correctly, and I think I do, you're telling me it's going to be 18 times the square root of 1 minus 0.95 squared. The c's would cancel. 18. Am I expecting this to be shorter or longer at relativistic speeds? What happens to lengths as we speed up? Okay, they get they get shorter. Time gets bigger, slows down. Mass gets bigger, length gets shorter. Distances get shorter. You get 5.62, is that right? No, yes? Yep. 5.6, I'd take that. I'll go 5.62. Meters, same as before. Half mark, 1 mark, half mark. But again, if you got the right answer, 2 out of 2. Oh, time. Is part B asking me to find t or t0? In the time equation, was t0 time on the spaceship or time back on Earth? On the spaceship. So is this question asking me to find time on the spaceship or time back on Earth? Oh, this is asking me to find t0. So that must mean that 5 is t, and v was 95% of c. Well, the time equation looks like that. I want to get the t0 by itself, Ethan. How would I do that? How will I move that big square root over? What's this big square root doing to the t0? Adding, subtracting, multiplying, or dividing? So how will I move that square root over? Yeah. Okay. You can memorize, you know what? If you get good at the formula manipulation, you really don't have to memorize a lot of this crap, right? So if I hear you correctly, Ethan, and I think I do, you're telling me it's going to be t times 1 minus v over c all squared? Say yes. There you go. So you're telling me the time on the spaceship, 5 hours on Earth, 1 minus, the c's would cancel yet again. 5 times the square root bracket 1 minus 0.95 squared. About an hour and a half, little more than 1.56 hours, little over an hour and a half. Okay. Since we had to redo an equation, I would give you 1 mark for the correct equation, half mark for the numbers, half mark for the answer, and then I'd, turn the page. Yeah. Joseph, what's number 6 asking me to find? What letter has that been in our equations? C. Nope, that's the speed of light. That doesn't change. That's a constant. V. Don't listen to Evan. He just sucked you in. Okay? Now, problem. I didn't give you, and we didn't write down, the equation for speed, Robbie, for a mass. But, Robbie, doesn't the mass equation look just like the time equation? And we did write down the speed for the time equation. I hope. I told you guys to. Yes? So can somebody... what's the speed? I think I can use that equation, but just replace every t with an m. I know it looks like this. That's all I know. Mariah's going to put her phone away completely because she's not that important. Face down. Thanks, kiddo. Is it times the square root or divided by the square root, the v equation? Is it times? And I know it's still 1 minus. It's either m0 over m or it's m over m0 squared. Which one? Is that what it is in the time equation? So it's t0 over t, so it's going to be m0 over m all squared. Is that right? Okay. So it's going to be 3 times 10 to the 8th, there's the speed of light, square root of 1 minus, what's m0? 2 or 4? 2 over 4 squared. By the way, 2 over 4, if you wanted to, you could just say 0.5, because that's what it is, squared. So I'm going to get 3 scientific notation button 8 times the square root of 1 minus 0.5 squared. That's what 2 over 4 is as a decimal. I get that. 2.6 times 10 to the 8th. I'm going to go 2.598 times 10 to the 8th, but I would take 2.6 times 10 to the 8th. Or, if you left it as a percentage of the speed of light, because I didn't specifically say, divide by 3 times 10 to the 8th, and we get 0.866 C, or 86.6% of the speed of light. I'd take either of those, Rylan. On the test, I'll be clear, there will probably be 2 velocity questions on the test, and I bet you in one of them I'll say, give your answer in meters per second, and in one of them I'll say, give your answer as a percentage of the speed of light. Okay? Maybe 3 velocity questions, but probably 2. Gonna make it, Cody?
No.
Nice yawn. Ah! No? Nothing? I'll get you yet. Number 7. I like number 7. I like number 7. I like number 7. First of all, it's cool because, holy smokes, it's that different for the space astronauts compared to the Earth? Yeah. Simone, what's part C asking me to find? I could actually do C right now without doing A and B. I could actually use the length equation where I could say on the Earth at rest, the length is 40 light years, square root of 1 minus, the spaceship is traveling at 99.5% of the speed of light. Jared wants me to say the C's will cancel. I agree. You could actually get the distance using that. 40 square root of 1 minus 0.995 squared. So even though we think it's 40 light years away, holy smokes, they're going to say it's 3.995. If you said 4.0, I'd take that. I'm going to go 3.995 light years. But I'll also, Justin, show you the long way to get there. The long way to get there starts with part A. Part A says, how long do we think it takes on the Earth? Well, since we are at rest, we would actually go like this. Time is the distance divided by the velocity. That's from d equals VIT plus a half AT squared. If you cross out the AT squared because it's 0, you have d equals VT, get the t by itself, divide by v. The distance is 40 light years, and the speed is 0.995 c. Dylan, what does the letter C stand for? You can sort of say that that light and that light cancel, and you're going to get an answer in years. That's kind of bad unit analysis, but it works. It's going to be 40 divided by, you know what? They're almost traveling the speed of light. If they were traveling at the speed of light, it would take them 40 years. It takes them a little bit longer, but not much. 40.2 years. What about on the spaceship? Well, now they want me to find when t equals 40.2. Oh, and v equals 0.995 c. I think we already redid the t equation. We said, sorry, the t0 equation. We said it was t times 1 minus v over c all squared. It's going to be 40.2 times 1 minus 0.995. Oh, you know what? Jared wants me to say the C's will cancel, so I don't need to bother writing them. I agree. I'm going to use my answer button, because it's not 40.2. It's actually 40.20100. That times the square root of 1 minus 0.995 squared. And I get that the people on the spaceship, even though to us it takes them over 40 years, to them the trip lasts 4.015 years. It's a very short trip for the astronauts. Then, if you wanted to, Mariah, for part C, you could go distance equals speed times time. Which speed? 995c. Which time? 4.015 years. Dylan, what did the letter C stand for? Can you see, actually, we're going to get light years if I just multiply the numbers together. So I'm going to take this number and times it by 0.995, and I'll bet you we get the same distance. In fact, what we've really just done is we proved the length equation works based on the time equation. Let me write this down first, and then I'll take questions. Now, I would take a 4 there or a 3 there, depending on how you round it off. I used my answer button. If you round off that second or third, certainly that third or fourth decimal place might be a bit off, and I'd accept that. Question?
That was my question.
I figured so. I know, I've done this before. I know my audience. Okay? So your test is going to be the first quiz, the second quiz, a couple extra questions from the homework. I think that'll be it. Is that all right? Your test is next class. Can you give yourself a score, please, out of 20?
We only have like 4 assignments this term, right? Lesson 2 and 3.
Lesson 1 of the next unit, Newton's laws of motion. First of all, if you want me to give you a definition of a force, Cody, I would say a force is a push or a pull. There are better, more complicated definitions. In fact, technically, there's only 4 fundamental forces, which means, Justin, that most of the stuff I'm teaching you is actually combinations of all those forces. You can go all the way down to the quantum level if you want to. We're not going to, Duncan. We're going to stay up at a higher level. We're not going to get into the really nuts and bolts, meat and potatoes. Force, vector or scalar, it's absolutely a vector. Direction makes a huge, huge, huge difference. It's a vector. Symbol for force. What would be a good letter to use for force? Capital F. And I'll put the vector symbol above it just to remind myself, hey, it's a vector. That's going to be important. Units. Force is measured in newtons. Symbol capital N. Yes, it's named after Sir Isaac Newton, and because you're going to see much of this unit is named after him. Today's, we're going to be talking about Newton's laws of motion, and I'll go on a Sir Isaac Newton story rant. One of the things that we're going to be asking ourselves, and you can underline this phrase, is finding the net force. Now, the word or the phrase net force, what that really means is if you add up all the forces and replace them with one thing, the single overall force on an object. So we're going to start off relatively not too bad, and then get yuckier. So here's a picture. I have a force 5 newtons to the right. I have another force 2 newtons to the right. What would you say, based on your understanding of physics, the net force is? Make a guess. Direction. 7 newtons to the right. In other words, Evan, 5 plus 2 is 7. Not always. Here's another picture. I have 5 newtons to the right, 2 newtons to the left. What do you think the net force here is, Evan? 3, direction? So in this case, 5 plus 2 gave you 3. In the previous case, now you might be saying, no, Mr. Duick, I went 5 minus, I think what you actually did is 5 right plus 2 left. And then you said, I can treat left like a negative mathematically. What we're going to be talking about is some vector mathematics. 5 plus 6 is not always 11 when we're talking about vectors. 5 plus 2 is not always 7. It's not always 3 either. It can be anything in between. Part C, this next one, this is a very, very important situation. If you know this situation, you can make a bunch of other conclusions. What's the net force here? 0. If you know the net force is 0, in a couple of days, you'll automatically know a whole bunch of other stuff. D. Ariel went like this. No, you're right. You know what? If you take Physics 12 next year, you'll find we'll do most of Physics, the first third of the course is Physics 11 done over again, but in 2 dimensions. We're not just going to keep everything in a nice straight line. What if you're pushing to the right and pushing up at the same time? Now, as a preview of coming attractions, Shayna, I'll tell you what we do. We would actually go like this. We would say, that's the answer. We would use Pythagoras to find how long it was. And then we would use SOHCAHTOA trig to find an angle. And we would say, oh, if you push with 6 newtons to the right and 3 newtons up, you'll actually end up pushing with however big that is at whatever angle that is. If you take Physics 12 next year, you'll get better at trig than you ever thought possible. You'll find trig becomes almost like your times tables where you're like, you know what, I'll show work on a test just to make sure I don't make a mistake, but in my homework, I'm doing this all on my calculator, not bothering to do the work. So we got to go on my Sir Isaac Newton rant. Newton's laws of motion. Put your pencil down. Newton's first law, it's often called the law of inertia. In the absence of an unbalanced net force, an object will either, only 2 options, remain at rest or move in a straight line at a constant speed. Or Shane, if I want to phrase it a different way, it won't accelerate. If an object is accelerating, there has to be an unbalanced force on it. The net force can't be 0. That's Newton's first law. So right now I look at Jaden here in the front row. I say, Jaden, are you accelerating? You're sitting still. I guarantee the net force on you is 0. Wait a minute, Mr. Dewick. Isn't gravity pulling him down? Yeah, but that must mean there's another force pushing you up. Otherwise, you would have to be sinking into the ground like quicksand. When you jump, all you do is you create a slightly bigger unbalanced force than gravity, and therefore you have to accelerate up because you've got an unbalanced force pointing up. That's how it works. This is Newton's first law. Or if you've ever been in a car that's made a quick left turn, you might have felt like you were getting pushed into the door. That is not what's happening. In real life, you are going in a straight line. Your body wants to keep going in a straight line. And what happens is the car is moving underneath you. You keep going in a straight line, and right here, the car has to apply a force to get you to turn. This is Newton's first law. You think you're getting forced into the door. No. It's the door pushing against you to make you turn the corner. This is why, Jared, I said all those months ago that our bodies are backwards accelerometers. We can feel it, but it's always in the opposite direction. It's because really what we're feeling is our own inertia, our own resistance to a force. If you talk to your grandfather, he may admit this. Back in the 1960s, all the teenage boys knew this. Back then, all the cars had bench front seats, and nobody wore seatbelts. So if you were going out on a date, what guys would do, ask your grandfather, either he did it or he'll know a friend who did it, they would take surfer's wax and they would wax down the passenger seat. And then you would be driving and you would sit with your arm like this and you would make a quick right turn. And the girl would come sliding across and, oh, hi, honey, well, hi, very nice. Okay? No, the girl didn't come sliding across. The girl kept going in a straight line. The car moved underneath her. Her inertia kept her going in a straight line. It was the car that was moving, but relative to the driver, it seemed as though she had come into his arms. She had moved in next to him. Ask your grandfather. He might admit it, I'm telling you. So, contrary to what your common sense might tell you, you're not being pushed to the right at all. You're wanting to keep going in a straight line, and it's the car having to apply a force on you to get you to move around the corner. Your body wants to keep going on its original path. Why? Because it has inertia. I know I haven't defined what inertia is yet. Let's do that. So, next page. Here's what Newton said. Evan, he said, as a rule, an object wants to keep moving with whatever speed and direction it presently has. In fact, we like to say it resists change to its motion state. It wants to keep going in a straight line at a steady speed. This can also include zero speed as well. So if it's at rest, it wants to stay at rest. Newton phrased it this way: objects at rest tend to remain at rest. Objects in motion tend to remain in motion, which is really a confusing way. Here's what I'm saying. Joseph, if you want something to accelerate, which means either change its speed or its direction or both, you have to apply an unbalanced force. And if it's not accelerating, there is no unbalanced force. The net force is zero. When your driver accelerates a car, your body wants to stay where it is. And so you feel the seat having to push you forwards, but you think you're getting pushed backwards. This is why our bodies are backwards accelerometers. This tendency that all massive bodies have to resist change in their motion state has a special name. We call that inertia. The more inertia an object has, the harder it is to get it to accelerate. Every object in the universe that has mass possesses inertia. Another way to think about it, inertia can be thought of as a measure of the laziness of an object. The more inertia it is, the harder it is to get it to do anything. It's lazy. Or its resistance to change. Just that rule alone, Evan, explains a lot of stuff that you've taken for granted. What? Yeah. Robbie, what has more inertia, a bicycle or a logging truck? Let's circle that. Now, what does that mean? That means, and that explains why, Robbie, because the logging truck has so much more inertia, it's more difficult to get moving. That's why if you've ever been at a red light behind a semi-truck, they don't accelerate very fast. It's not to do it. It's not the engine. They have more inertia. We'd have to build massive engines to get them to accelerate. We're not going to do that. It means, Robbie, they're also more difficult to stop. And it means they're more difficult to turn at a corner. They don't corner as well. Now, you've picked up on this as you've started driving, as you've noticed vehicles. You've clued in, a little Austin Cooper can stop a lot faster than a logging truck. But this is why. Because the logging truck possesses this thing that we've called inertia. Except I haven't told you how we measure inertia. How do we measure inertia? In fact, Rylan, I'm going to say for Physics 11 and for Physics 12, we're going to use mass and inertia interchangeably. That isn't technically right, especially when you get to relativistic speeds, but it's going to be right this year. The more mass an object has, the more inertia it has. And if you want to know how much, tell me its mass in kilograms. Inertia, or mass, resists a force. You can think of it as the measure of the laziness of an object. The more mass an object has, the less willing it is to change its motion state. Oh, Jaden, I did promise that I would use you as a guinea pig. So that's how the trick with the tablecloth is done. Oh, Joseph and Mariah, you may have noticed I was very careful. I didn't yank up. In fact, I yanked straight down and I used the counter as a fulcrum to make sure all the force was sideways. If I had lifted up, that would change the situation. Then Jaden might have got wet. You can try that if you have an old set of dishes with a tablecloth. Google some tips on how to do it first. But the trick is you yank the tablecloth down, you let the table itself bend the cloth, and your cloth also can't have a hem on the far end because that'll catch the dishes. But otherwise, you can do that trick. It's not any camera effects. You can do it. It's a good physics trick. I wrote down here car accident story. In 1996, I was on the Trans-Canada Highway by the Burnett exit, and I got rear-ended by a semi-truck. Yeah, it hurt. But it was beautiful physics. So Here's what I saw. I was driving a 1982 little Honda, and I had an ashtray that I was keeping all of my change in. And when I got rear-ended by the semi-truck, the ashtray went shooting over my shoulder and hit the back seat. Or did it? That's not what happened. That ashtray, Evan, had enough inertia, enough mass, that actually, when I got rear-ended, my car shot forward. The ashtray just stayed where it was. But relative to me, because I was in my car and my car was accelerating forward, I thought it shot over my shoulder. No. It stayed in one place. My car was what left it behind. Inertia, this idea that an object with mass wants to keep going in a straight line at a steady speed. Put your pencils down. So, Newton's first law, what he tried to explain was, there's a reason objects on the earth tend to slow down. And that reason is there must be a force acting on them. Usually that force is friction. We'll get into that in more detail. If you haven't finished lesson 3, make sure you have that done for next class. If you haven't handed in or finished lesson 2, hand those in next class. You can hand them in today, but you can hang on to them to study.